To get a better understanding of how Bloom filters work, let's do some math and see how well they work. So remember, a Bloom filter works by having a bit array that starts as all zeros, but as you add items to the Bloom filter, some of these bits get set to 1. So let's say that the indexes of the bit array go from 1 up to m. Okay, now remember, a Bloom filter works by using a number of hash functions. So we're going to say that you have n hash functions, and recall each hash function takes an item as an input. So a hash function takes an item as an input and maps to a number between 1 and m. So I'm just going to write that, but remember that the hash function takes an item as an input, and the output is one of these indices, one of the squares in the bit array. So this is n hash functions, m bits in the bit array, and let's say that we're going to be adding k items to the Bloom filter. So we're going to look at how fast we can do this and how much space it takes up. One thing to point out right away is that it doesn't matter how big these items are. That won't affect the size of the Bloom filter, because every time you add an item, it's getting hashed down to just a number between 1 and m. And no matter how big the item is, the hash is always the same size. So the size of the Bloom filter is just m bits. I'm going to write that up here. And we'll see that this is actually really small compared to some alternate implementations of sets that we could be using. So let's now compute the probability that the Bloom filter gives a correct or incorrect answer. And as a first step in doing that, we'll try to write the probability that a particular bit, so let's just say bit I, is equal to 0. So a bit is going to be equal to 0 only if every time we've added an item, the bit was never set to 1. Because remember, bits start at 0 and they can be set to 1, but they'll never get set back to 0. So every time we add an item, there's n hash functions that get applied to it. And for one of these hash functions, if we assume the hash functions are uniform, that is, they have an equal probability of giving any one of these bits, then the probability that the bit is not flipped from 0 to 1 is m minus 1 over m, because there are m minus 1 out of m bits that would not result in this being flipped from 0 to 1. And because we're making an assumption that these, and I didn't mention this earlier, that these hash functions are both uniform and independent, because they're independent, we can multiply their probabilities. So when we apply n hash functions, the probability that none of them flip the ith bit from 0 to 1 is m minus 1 over m raised to the n power. And since we're inserting k items, this process happens k times, and so we raise the whole thing to the k power to get the probability that the ith bit is still 0, even after adding k items to the Bloom filter. So let's simplify this a little. This is equal to 1 minus 1 over m to the nk. And now I'm going to show you a trick that's handy often for this sort of math. And that is, I'm going to graph 1 minus x on this plot So this is x, this is the y-axis. So 1 minus x looks like this. And I'm going to graph e to the negative x, which is going to look, it's going to be tangent at 0 and tangent to the x-axis as you go up to infinity. So this is e to the negative x. And you'll notice that for all values of x, 1 minus x is less than or equal to e to the negative x. And this inequality comes in handy quite a bit. You notice equality happens at 0, where 1 minus 0 is 1, and e to the negative 0 is also 1. In addition to that, both curves have the same slope at 0. So we're going to use this inequality now. 1 minus 1 over m is going to be less than or equal to e to the negative 1 over m. E to the negative 1 over m raised to the nk, you get nk over m, and this is less than or equal to that. And so we have a result for the probability of any particular bit being equal to 0 after k items have been added to the Boom filter. Now the question we're really interested in is, what's the probability that contains says true for a random input? So this is going to be the probability that the n hash functions for the input are all set to 1. So that's going to be the probability that a single one of them is set to 1 is 1 minus this. And the probability that all n of them are set to 1 is this raised to the n power. And so this is the probability that you're just going to get true regardless of what the input is. And so in the next video, we'll try to get some intuition for exactly how these Boom filters behave.